Welcome to Context Engineering in LLMs, moving beyond prompt engineering. We're launching this series to explore a fundamental shift in how we build intelligent systems, a move away from simply talking to an AI and toward designing the world it thinks within.
Exactly. For the past few years, the conversation has been dominated by prompt engineering. It's been treated as a kind of modern-day alchemy, a dark art of crafting the perfect incantation to get a large language model to do what you want. But what happens when that single magic spell isn't enough? What happens when the task is too complex, too long-running, too dependent on information the model wasn't trained on?
That's the core question we'll be tackling. It marks an evolution in our thinking, from the craft of the prompt to the architecture of context. In today's inaugural episode, we're laying the groundwork for this entire series. We'll start by dissecting the inherent limits of prompt engineering as a standalone discipline.
From there, we'll formally define this new, more holistic approach we call context engineering. We'll explore a powerful analogy that frames the LLM as a new kind of operating system, which really clarifies the role context plays. This will lead us into a deeper discussion on precisely why curated context is the bedrock for building reliable and trustworthy AI.
And finally, we'll look at some of the pioneering systems that paved the way for this new paradigm, like retrieval-augmented generation, or RAG, and the first wave of agent frameworks. These early examples showcase a move from static, pre-trained knowledge to dynamic, runtime information.
This isn't just an academic distinction. Understanding this shift is critical for anyone building serious applications on top of LLMs. It's the difference between building a clever toy and engineering a robust, scalable, and coherent AI system. So let's begin with the cracks in the foundation, the limits of prompt engineering.
When we first started interacting with models like GPT-3, the idea of getting a machine to write a sonnet or a piece of code with a simple instruction felt like magic. But as we've moved from these single-shot tasks to more complex, multi-turn interactions, the magic starts to wear off. The reality is, a prompt is a fleeting thing.
It's a great starting point, but it's like trying to build a skyscraper with only a hammer. A prompt is a single tool, but complex problems require a full toolkit. The core issue is that LLMs are, by their very nature, stateless. Each time you interact with one in a basic API call, it has no memory of your previous conversation. It's a brilliant but amnesiac processor. We create the illusion of memory by refeeding the entire conversation history back into the model with every new turn.
And this leads directly to the problem of the context window, which is essentially the model's short-term memory, or its RAM. Everything the model knows for a given task, your instructions, your data, the conversation history, has to fit into this finite space. Simply stuffing more and more text into the prompt as a workaround is a brittle strategy.
It's incredibly brittle. As the context window fills up, models can lose focus. Important instructions given at the beginning can get lost in the middle. The model's attention isn't uniform across the entire context. This degradation of performance is a well-documented phenomenon. You're trying to have a coherent, long-form conversation, but the model starts forgetting the premise of the discussion. It's like talking to someone who can only remember the last 2 minutes of your conversation.
This is where the need for a more structured approach becomes painfully obvious. We need to move beyond just writing better prompts and start designing better information environments for the model to operate in. And that brings us to the core of our discussion: defining context engineering.
Context engineering is the systems-level discipline of designing, curating, and managing the entire information ecosystem that an AI model interacts with. It's a paradigm shift. Instead of focusing on the instruction, the prompt, we focus on the environment. This environment includes not just the immediate instructions, but also relevant data, persistent memory stores, and access to external tools.
So it's about architecting the entire information flow to and from the model, ensuring that at any given moment, the model has precisely the right information in its limited context window to perform its task effectively. It's not just what you say to the model, but what information you make available to it and how you structure that access.
Think of it this way. Prompt engineering is like writing a single, very detailed email to a new employee with a one-time task. Context engineering, on the other hand, is like designing their entire onboarding process. You're not just giving them one task, you're giving them access to the company handbook, introducing them to the right team members, showing them where to find shared documents, and providing them with the software tools they need to do their job on an ongoing basis. You're building a supportive ecosystem for them to succeed in, not just handing them a to-do list.
That's a fantastic analogy, and it connects perfectly to this idea popularized by Andrej Karpathy, the former head of AI at Tesla, who proposed we think of large language models as the CPU of a new kind of computer.
It's a really powerful mental model. If the LLM is the central processing unit, the engine of reasoning and generation, then its context window is the RAM, the random access memory. It's the fast but volatile and limited workspace where the CPU does its active thinking. You can't fit your entire hard drive into your RAM. You have to be selective about what you load into it.
Exactly. And if the LLM is the CPU and the context is the RAM, then context engineering is the practice of building the operating system. The OS's job is to be the master resource manager. It decides which programs and data to load from the long-term storage, the hard drive, into the limited RAM for the CPU to work on right now.
A great operating system is incredibly efficient at this. It anticipates what the CPU will need next and prefetches it. It swaps out old, irrelevant data to make room for new, critical information. It manages the flow of information seamlessly so that the CPU can perform at its peak without getting bogged down or working with stale data. That is precisely what a good context engineering pipeline does for an LLM. It manages that precious finite RAM, the context window, to enable the highest quality of reasoning from the LLM CPU.
This really reframes the entire challenge. It's no longer about cramming a 100-page document into a prompt and hoping for the best. It's about building a system that can intelligently retrieve page 73, paragraph 4, because it knows that specific piece of information is what the model needs to answer the user's current question.
And this directly addresses why context is so fundamentally important. The quality of an LLM's output is not just a function of the model's intelligence, but a direct consequence of the quality of the context it is given. Without the right context, these models are prone to hallucination.
Which is a polite way of saying they make things up. And they do it so confidently. A model might not know the current CEO of a company, but because its programming is to generate the most probable next word, it will confidently invent a plausible-sounding name rather than say, "I don't know."
But if you provide it with the right context, for instance by giving it the result of a real-time web search or a snippet from a company's internal database, it doesn't have to guess. The context provides the ground truth. It constrains the model's possible outputs to the facts you've provided. Curated context acts as a set of guardrails, keeping the model on task and tethered to reality.
This boosts accuracy, but it also fundamentally increases trustworthiness. If you're building a customer service bot, you can't have it inventing your company's return policy. It needs to be fed the actual policy document. If you're building a medical AI, it needs to be grounded in the latest peer-reviewed medical literature, not just the generalized information it was trained on years ago.
The context is the anchor. Without it, the model is a brilliant but untethered mind, capable of incredible feats of creativity and reasoning, but with no reliable connection to the real world. Context engineering is the art and science of forging and maintaining that connection.
And this isn't just a theoretical concept. We've seen the principles of context engineering in action for a while now, even if we didn't always use that specific term. Early systems like retrieval-augmented generation, or RAG, are perfect examples.
Absolutely. RAG was a groundbreaking step because it was one of the first widely adopted techniques to systematically address the LLM's knowledge limitations. The core idea is simple but powerful. Instead of relying solely on the model's static, pre-trained knowledge, which can be out of date, you augment it with fresh, relevant information at the moment of the query.
So when a user asks a question, the system doesn't immediately pass the question to the LLM. First, it uses the question as a search query to retrieve relevant documents from an external knowledge base, a vector database, a traditional search index, a product catalog, anything.
Then it takes the most relevant snippets from those retrieved documents and injects them directly into the context window, right alongside the user's original question. It essentially says to the LLM, here is the user's question, and here are a few paragraphs of text that likely contain the answer. Now, please answer the question based on the information I've just provided.
This is context engineering in its most classic form. You're not just prompting the model, you're actively managing its context by fetching and inserting real-time factual data to guide its response. You are, in effect, building a simple operating system that loads relevant files into the model's RAM before asking the CPU to process a task.
Agent frameworks are another great example. Systems like LangChain or Llama Index provide developers with the tools to build these context pipelines. They make it easier to chain together different steps, receive a query, search a database, call an API for live data, process the results, and then assemble all of that information into a structured context for the LLM.
These frameworks allow an LLM to interact with the outside world through tools. Giving a model a tool, like a calculator or a web search API, is a form of context engineering. You're not just giving it static information, you're giving it a capability. The context then includes not just data, but also the potential to generate new data by executing a tool.
This all points to the same fundamental conclusion. The future of building with AI is not in creating a single, monolithic, all-knowing model. It's in designing intelligent systems that artfully weave the reasoning power of the LLM with the vast, dynamic information of the outside world. The magic is not in the prompt alone. It is in the architecture of the system that surrounds it.
So, to summarize, we've established that relying on standalone prompt engineering is a dead end for complex applications due to the stateless nature of LLMs and their finite context windows. It's simply too brittle.
And we've defined context engineering as the necessary evolution, a systems-level approach to designing the entire information environment, data, memory, and tools that an AI operates within. It's the art of building the operating system for the LLM CPU.
This curated context is what transforms a creative but unreliable generator into a focused, accurate, and trustworthy reasoning engine. It's the key to mitigating hallucinations and building systems we can actually depend on.
And early examples like RAG and agent frameworks have already proven the power of this approach, demonstrating how to dynamically inject external knowledge and capabilities into the model's workflow at runtime. It's a fundamental shift from prompting to architecting.
So, to summarize, we've laid the foundation for what context is and why it's the new frontier. But this immediately raises a critical practical question. We've talked a lot about the context window being the model's finite RAM. If that space is so limited, how do we effectively manage it, especially as conversations and tasks grow in complexity? How do we give our AI a persistent memory that extends beyond a single interaction?
That is the crucial next piece of the puzzle. Managing that finite attention budget is perhaps the single biggest technical challenge in building sophisticated AI agents today. And that's exactly where we'll be going in our next episode. We'll dive deep into the mechanics of memory and retrieval, exploring techniques like advanced retrieval pipelines, persistent memory architectures that allow an AI to learn over time, and strategies for compressing and prioritizing information to make the absolute most of every single token in that context window.
Welcome to Context Engineering in LLMs, moving beyond prompt engineering. In our last discussion, we framed the large language model not just as a text generator, but as a powerful CPU. We explored how, like any processor, its performance depends entirely on the data loaded into its RAM, its context window.
Exactly. We established that simply stuffing that window with more and more instructions, or what's known as prompt engineering, quickly leads to diminishing returns. It's like shouting a long, convoluted order at a brilliant but amnesic chef. They might catch the first few ingredients, but will likely forget the rest. This is where the real work begins, moving beyond the single prompt to architecting the entire information environment.
That brings us to the core challenge we're tackling today, the inherent limitation of that very RAM. What happens when the task at hand requires more knowledge than can fit into a single context window? How do we give these models a sense of continuity, a memory that persists beyond a single interaction?
This is the critical next step in building truly intelligent systems. Today, we're exploring memory and retrieval, extending the context window. We'll be dissecting the problem of finite context windows and the concept of context rot. From there, we'll move into the foundational solution, retrieval-augmented pipelines.
We'll then go deeper, looking at architectures for persistent memory, allowing an AI to learn and recall information across conversations. We will also contrast static, read-only context with dynamic, writable memory, which allows the AI to evolve its own understanding.
And finally, we'll touch upon some advanced strategies for managing this memory, including hierarchies and compression techniques. Think of it as moving from a model with the memory of a goldfish to one with a library, a journal, and a system for organizing it all. This isn't just an upgrade, it's a fundamental shift in how we design and interact with AI.
Let's start with the root of the problem, the finite context window. Every LLM, from the smallest open source model to the largest proprietary ones, has a hard limit on the number of tokens it can process at once. This isn't just a matter of computational cost, it's a core architectural constraint. As you fill this window with more text, more conversation history, more documents, more instructions, the model's ability to pay attention to all of it degrades.
This degradation is what's often called context rot. It's a very intuitive phenomenon. Imagine you're reading a dense 1,000-page novel. By the time you reach the final chapter, you've probably forgotten the name of a minor character introduced on page 20. The LLM experiences something similar. The critical piece of information it needs to answer a query might be buried at the beginning of a long conversation. The further back it is, the higher the chance the model forgets or overlooks it, leading to a loss of coherence or factual errors.
This is often referred to as the lost in the middle problem. Studies have shown that models tend to recall information from the very beginning and the very end of their context window, much more reliably. For a system that needs to maintain a consistent state or follow a complex multi-step instruction set, this is a catastrophic failure point. You can't build a reliable system if its memory is fundamentally unreliable and its attention is fickle.
It's like trying to have a serious debate with someone who only remembers the first and last thing you said. You'll find yourselves going in circles with no real progress. The practical implication for developers is that you can't just keep appending the entire chat history to the prompt and expect the model to perform well. At some point, performance won't just plateau, it will actively get worse. The model gets bogged down in irrelevant details, and its finite attention budget is squandered.
Which leads directly to the first major innovation designed to solve this, retrieval-augmented pipelines, or RAG. If the model can't hold all the necessary information in its active memory, then the system needs to be smart about what information it provides and when. RAG is the mechanism for doing just that.
I like to think of a RAG system as a hyper-efficient research assistant working for the LLM. The LLM is the brilliant thinker, but it doesn't have the entire library memorized. When a user asks a question, the LLM doesn't try to answer from its limited internal knowledge alone. Instead, the RAG system first takes the query and identifies the core concepts.
This is typically done by converting the user's query into a numerical representation, an embedding. This embedding is a vector that captures the semantic meaning of the query. The system then uses this vector to search a vast external database, a vector database, which contains chunks of documents that have also been pre-converted into embeddings. The search finds the document chunks whose embeddings are closest and therefore most semantically similar to the query's embedding.
So our research assistant isn't searching for keywords, it's searching for meaning. It finds the most relevant paragraphs, articles, or data entries from its library. Then it takes these retrieved documents and presents them to the LLM, right alongside the original question. The prompt becomes something like, "Given these following facts from our knowledge base, please answer this user's question." The LLM now has the specific, relevant information it needs loaded directly into its short-term memory, its context window, to formulate a precise and factually grounded answer.
And this is revolutionary because it decouples the model's learned knowledge from its ability to access new information. The core LLM doesn't need to be retrained every time a new company policy is written or a new product is launched. You simply add that new information to the vector database. The RAG pipeline ensures that the model always has access to the most current, up-to-date facts at the moment it's generating a response. It's a way to keep the model perpetually informed without the immense cost of retraining.
But RAG, in its basic form, is still a form of read-only memory. The LLM can read the documents it's given, but it can't add to them or change them. It learns nothing from the interaction that persists into the next one. After answering the question, that context is gone. To build a truly adaptive agent, we need to go a step further and design for persistent memory.
This is where we introduce architectures that allow the agent to save and reuse knowledge outside of the immediate prompt. Think of it as giving the AI a notebook or a long-term memory store. The simplest form of this is a scratchpad. During a complex reasoning task, the model can output its intermediate thoughts, calculations, or plans. The system saves this to an external file or buffer and then feeds it back into the context for the next step. This allows the model to build a chain of reasoning without trying to hold it all in its head at once.
A great example is a customer service agent. With a simple RAG system, the agent can look up order details, but with persistent memory, it can remember you. After a conversation, the agent could generate a summary. The user expressed frustration with shipping times and is interested in products from category X. They prefer a formal tone of communication. This summary is then saved, perhaps as an embedding, in a user profile database.
The next time that same user starts a chat, the system first retrieves that summary. The initial prompt to the LLM would be something like, "You are speaking to a returning user. Here's a summary of your last interaction. Insert summary." The user's new query is, "I need help with another order." Suddenly, the agent has continuity. It can reference past issues, tailor its recommendations, and remember preferences. This transforms the user experience from a series of stateless, repetitive transactions into a single, evolving relationship.
This brings us to a crucial distinction: the difference between static and dynamic context. Traditional RAG, as we've said, provides a static, read-only knowledge base. The library of documents is curated by humans and is fixed from the model's perspective. It's a source of truth, but it's a one-way street. The model consumes it, but cannot contribute to it.
Advanced context engineering, however, pushes for dynamic memory. This is context that the agent can actively update, overwrite, or add to over time. The model is given the ability to write back to its own knowledge stores. This is a paradigm shift. The AI is no longer just a reasoner, it's a learner. It can update its own understanding of the world, a user, or a task based on its interactions.
Imagine an AI system managing a complex project. A static RAG system could provide it with all the initial project plans and documentation, but as the project evolves, tasks are completed, new problems arise, and deadlines shift. With dynamic context, the AI can be given a tool that allows it to update the project status in a database. When it completes a task, it can call a function to mark that task as done. When a new blocker is identified, it can add it to a risk log.
The system's own actions modify the context for its future self. The next time the AI is asked for a project update, it retrieves the current status from the database it has been maintaining. Its knowledge is no longer static. It evolves in lockstep with the real-world process it's managing. This creates a powerful feedback loop where the model's outputs become its future inputs, enabling genuine stateful and adaptive behavior.
This dynamic capability, of course, introduces complexity. We now have all this information: the conversation history, retrieved documents, persistent user memories, scratchpad notes. If we try to stuff all of that into the context window, we end up right back where we started, with context rot. This is why the most sophisticated systems employ memory hierarchies and compression techniques.
Exactly. It's not practical to load the entire history of every interaction into the prompt every single time. Instead, we need a multi-level caching system for context. At the most immediate level, you have the short-term buffer, the last few turns of the conversation. This provides immediate conversational flow.
Think of it like your own mind. The short-term buffer is what you're actively thinking about right now. It's fleeting but highly relevant. Then you have a middle tier of memory, which might be a summary of the current conversation. Every 5 or 10 exchanges, the system can use another LLM call to generate a concise summary of what's been discussed and what the key conclusions are. The raw turn-by-turn dialogue is then replaced with this much denser summary.
This is a form of context compression. You're pruning irrelevant details, the ums, the ahs, the conversational pleasantries, and retaining the core semantic information. You maximize the useful signal per token. The old dialogue is then archived into a long-term storage, perhaps a vector database, where it can still be retrieved by similarity search if a very specific detail from a past conversation becomes relevant again.
It's a full hierarchy. You have the immediate raw history as a fast access cache, you have compressed summaries for medium-term recall, and you have the full searchable archive for deep long-term memory. The context engineering system acts as an orchestrator, deciding at each step what combination of these memory sources is most relevant to the current task. It might pull the last 2 chat messages, the summary of the current session, the user's persistent profile, and a few highly relevant documents from the RAG store.
This intelligent management of the context window is what allows the system to scale. It maintains focus, avoids context rot, and brings the most pertinent information to the forefront of the model's attention, right when it's needed. It's the difference between a cluttered desk with papers everywhere and a perfectly organized filing system where the right document is always at your fingertips.
So we've journeyed from the fundamental problem of a finite window to a sophisticated, multi-layered solution. We started with RAG as a way to inject external facts, then evolved to persistent memory to give the AI continuity, and finally arrived at dynamic, hierarchical systems that allow the AI to not only recall, but also to learn and manage its own evolving knowledge base. This is the foundation for building agents that can handle truly long-running, complex, and personalized tasks.
It's a profound shift. We're no longer just prompting a model. We're designing its entire cognitive architecture. We're building its memory. And how we structure that memory, how we design its retrieval, and how we allow it to be updated will be the defining factors in the capability and reliability of the next generation of AI systems.
That's a perfect place to leave it for today. We've established the what and the why of memory and retrieval. The next logical question is how. How do we actually build these systems? What do the architectures look like?
And that's exactly where we'll be heading in our next episode. We will explore architecting context, pipelines, tools, and orchestration. We'll get our hands dirty with the design patterns, from RAG pipelines and tool integration to the controllers and frameworks that manage the flow of information, orchestrating the dynamic and static context we've discussed today. We'll look at the plumbing that makes all of this possible. Welcome back to Context Engineering in LLMs, moving beyond prompt engineering. In our last episode, we explored the critical role of memory, discussing how retrieval augmentation and persistent memory architectures help us overcome the finite context windows of today's models. We established that for an LLM to be truly effective, it can't just rely on a single prompt. It needs access to a history, a knowledge base.
Exactly. But that raises the next logical question, and it's a big one. It's not enough to just have all this information. The instructions, the data, the memory, the tools. How do we get the right information to the right time? This is where we move from simply filling the context window to architecting it. We're transitioning from being prompt engineers to becoming true context engineers.
That's the perfect way to frame it. Today, we're diving deep into the architectural patterns that make this possible. We'll start with the foundational concept of retrieval-augmented generation, or RAG, as a data pipeline. Then we'll explore how to weave in tools and memory to give the model capabilities beyond text generation.
And we'll get into the really fascinating part, the orchestration of it all. We'll contrast static, predefined workflows with the more adaptive, dynamic loops we see in agent systems. This will lead us to a crucial discussion on balancing local, per-request context with a persistent, global understanding of the world.
Finally, we'll discuss a fundamental shift in philosophy, viewing context not as a mere input, but as the primary control plane for steering an LLM's behavior, often sidestepping the need for extensive fine-tuning. And we'll wrap up by looking at the emerging ecosystem of tools and frameworks like LangChain and Llama Index that provide the plumbing for these sophisticated architectures.
Understanding these architectural principles is what separates a simple chatbot from a robust, reliable AI system that can reason and act in complex environments. It's about building the scaffolding that allows intelligence to emerge.
Let's start with the cornerstone of many modern AI systems, retrieval-augmented generation, but viewed through an architectural lens. We often talk about RAG as a technique, but it's more accurate to think of it as a pipeline.
I like to think of a base LLM as a brilliant, highly trained chef who has read every cookbook in the world but is locked in a pantry with no fresh ingredients. They have immense knowledge of cooking techniques, the parametric memory stored in their weights, but they can't tell you what's on the menu today. A RAG pipeline is the system of sous chefs and runners that brings them fresh, relevant ingredients from the outside world just in time to cook.
That's a fantastic analogy. So, the first stage of this pipeline is understanding the customer's order, the user's query. This query is transformed into a representation, an embedding that our system can work with.
Right. Then the retrieval phase kicks in. The system uses that query embedding to search through its larder, which could be a vector database of documents, a knowledge graph, or even a set of APIs. It's looking for the most relevant ingredients, the chunks of information that will best satisfy the request. This is a critical step. The quality of what's retrieved directly impacts the final dish.
And once those documents or data points are retrieved, they are augmented into the prompt. We're not just passing the user's question to the chef, we're handing them the question along with a curated basket of the freshest, most relevant ingredients. This grounds the LLM, ensuring its response is based on factual, up-to-date information rather than just its generalized training data.
This pipeline approach is incredibly powerful because it's modular. You can swap out your retriever, update your knowledge base, or change how you chunk documents without having to retrain the entire LLM. It treats context as a dynamic data flow, ensuring the model is always working with the best information available at that moment.
But a truly advanced system needs more than just retrieval. It needs to do things. This brings us to the integration of memory and tools. How do we architect a system where the LLM can not only read information, but also use tools and write to its own memory?
This is where the operational loop comes in. Instead of a simple one-way pipeline, retrieve, augment, generate, we create a cycle. The LLM's output can now include a special kind of instruction, a function call. It might decide it needs to use a calculator for a math problem, query a database for sales figures, or call a web search API for current events.
So, the context we provide the model must include descriptions of the tools it has available, almost like a user manual. The model reads the user's query, looks at its manual, and says, aha, for this task, I should use the run_SQL query tool. It then generates the precise code to call that function.
Exactly. And the engineering part, the context engineering, is designing that loop. The system needs to be able to parse the LLM's output, recognize a function call, execute it, and then, this is the crucial part, feed the result of that tool use back into the context for the next step. The output of the calculator becomes a new piece of information the model can reason with.
This constant updating of the context is what separates a simple RAG system from a more dynamic, agent-like one. And this leads us directly to the idea of orchestration. We can have a very rigid, predefined sequence of these steps, which we might call static orchestration.
A static orchestration is like a factory assembly line. Step 1 is always to query the user profile. Step 2 is always to search the product database. Step 3 is always to generate a recommendation. It's predictable and reliable for straightforward, repetitive tasks. You define the context flow once, and it executes the same way every time.
But complex problems are rarely so linear. They require adaptation. This is where dynamic orchestration comes in. Here, we don't have a fixed assembly line. Instead, we have a supervisor or a controller that decides the next best action at each step based on the current state of the context.
Frameworks like LangGraph are a perfect example of this. They allow you to define your system as a graph, where different tools, retrievers, and LLM calls are nodes. The model itself, or a supervisory model, can then decide which path to take through the graph. It might start by searching documents, but based on what it finds, it might decide the next step is to use a tool or even to ask the user for clarification. The context is continuously being pruned, summarized, and expanded based on what the agent needs to accomplish its goal.
So dynamic orchestration is about giving the system the autonomy to build its own pipeline on the fly. This adaptability is essential for tackling complex, multi-step problems where the path to a solution isn't known in advance. It's a much more resilient and intelligent way to build.
And this brings up a fascinating design challenge, balancing what we call local reasoning versus global reasoning.
Explain that distinction.
Local reasoning happens within a single call to the LLM. It's all the information you can pack into one prompt: the user's immediate question, the retrieved documents, the recent chat history. It's ephemeral and task-specific. It's the model thinking, given this specific context, what is the next word?
Whereas global reasoning requires a much broader, more persistent context. This is the overarching knowledge that needs to span across multiple sessions or tasks. It could be the entire history of interactions with a user, a company's complete internal knowledge base, or a complex world state that the AI is trying to model.
Precisely. A robust system needs both. You need the local context to be sharp and focused to answer the immediate query efficiently. But you also need to be able to tap into that global context to ensure coherence and consistency over time. For example, a customer service bot needs the local context of the current problem, but it also needs the global context of that customer's entire support history to provide a truly personalized solution.
The architectural challenge, then, is designing systems that know when to fetch and integrate that global knowledge into the local context without overwhelming the model. You can't just dump the entire global state into every prompt. It's about intelligent retrieval and summarization at a macro level.
This leads us to one of the most powerful ideas in this field, using context as a control plane rather than relying solely on fine-tuning.
This is a really important shift in mindset. Traditionally, if we wanted an LLM to perform a specialized task, like acting as a legal expert, we would fine-tune it on a massive dataset of legal documents. We would bake the knowledge directly into the model's weights.
But that's a heavyweight and static process. The model's knowledge is frozen at the moment the fine-tuning ends. Context engineering offers a more dynamic alternative. Instead of changing the model itself, we change the information we provide it in real time. A general-purpose LLM can be turned into a legal expert for the duration of a single query by feeding it the relevant legal statutes and case law as context.
So RAG is a prime example of context as a control plane. We're guiding the model's behavior not by altering its parameters, but by shaping its information environment on the fly. This is far more flexible. You can update your legal knowledge base every day without ever having to retrain the model.
It's the difference between sending your chef to culinary school for a year to learn a new cuisine versus just handing them the right recipe and ingredients tonight. Both might result in a great meal, but the latter is far more agile and scalable. It allows a single, powerful generalist model to perform a vast array of specialized tasks simply by controlling its context.
To make all these architectural concepts a reality, a whole ecosystem of tools has emerged. It's the software for context engineering.
Absolutely. We're seeing the convergence of several types of tools. You have agent frameworks like LangChain and Crew AI, which provide the scaffolding for building these operational loops and orchestration logic. They help you chain together different components: models, prompts, tools, and memory.
Then you have specialized retrieval libraries like Llama Index and Haystack. While LangChain is more of a general-purpose framework, Llama Index, for instance, is deeply focused on the data ingestion and retrieval part of the RAG pipeline, optimizing how you index and query your knowledge base.
And we're even starting to see standards emerge for how these components talk to each other, like the idea of a Model Context Protocol, or MCP. The goal is to standardize the plumbing so that developers can focus on the high-level architecture rather than reinventing the wheel for data passing and state management every time.
It's important to remember that these specific libraries will evolve and change. The key takeaway for our listeners should be the enduring design principles they embody: modularity, state management, and observability. Building a system where you can easily swap out components and clearly monitor the flow of context is more important than committing to any single framework.
That's the perfect summary. We've moved from seeing the prompt as a simple string to understanding context as a complex living system. We've discussed how to build pipelines with RAG, how to integrate tools and memory into a dynamic loop, and how to orchestrate these flows. We've balanced the need for immediate local context with persistent global knowledge.
And most importantly, we've reframed our role as architects who use context as a real-time control layer to shape the behavior of powerful AI models. By mastering these patterns, we can build systems that are not just intelligent, but also reliable, adaptable, and grounded in fact.
Looking ahead to our next episode, we'll take these architectural building blocks and see what happens when they come to life. We'll explore the world of AI agents and modalities. We'll examine how these orchestrated context pipelines enable single agents to plan and execute complex tasks, and how multi-agent systems can collaborate by sharing and managing context flows.
We'll also venture beyond text, discussing how to integrate images, audio, and other data streams into the model's context, unlocking entirely new capabilities for AI to perceive and interact with the world. It's where the architecture we've designed today truly meets the complexities of the real world. Join us next time. Welcome to Context Engineering in LLMs, moving beyond prompt engineering. Last time, we laid the architectural blueprint for context, discussing everything from retrieval-augmented pipelines to the orchestration that makes them work. We looked at the plumbing of these new AI systems.
Exactly. We established the how, the frameworks and pipelines that structure information flow. But today, we're moving from the blueprint to the building in motion. We're asking what happens when that structured context becomes the lifeblood for autonomous, adaptive AI agents. This is where the true power of context engineering begins to surface, enabling behaviors that feel less like executing a command and more like genuine collaboration.
Today, we're exploring that dynamic frontier. We'll start with how a single agent uses context to create an adaptive loop of planning and action. Then, we'll scale that up to see how multiple agents can collaborate by sharing and managing context. We'll also venture beyond text into the realm of multimodal context, integrating inputs like images and audio.
And to make it all tangible, we'll look at real-world adaptive co-pilots and assistants that are already using these principles. Finally, we'll push the boundaries to distributed environments, like the Internet of Things, to see how context management works when it's not all neatly contained in one place. These aren't just incremental steps. They represent a fundamental shift from instructing a model to empowering an agent within a rich, evolving information environment.
Let's begin with the foundational unit of this new paradigm, the single-agent adaptive loop. At its core, this is about moving beyond a simple one-shot prompt and response interaction. Instead, we have a cycle. The LLM plans, it uses a tool, it observes the result, and critically, it updates its own context before the next step.
Think of it like a detective working a case. A detective doesn't just receive all the clues at once in a single file. They start with an initial lead, the first prompt. Based on that, they decide on an action, interview a witness. That's the tool use. The witness's testimony is the new information, the observation. A bad detective might just move on to the next witness, but a great detective stops, takes out their notepad, their memory, and writes. Motive seems to be financial, not personal. Need to check the victim's bank records next. That act of writing in the notepad is context engineering in action. The agent is actively curating its own information environment for the next reasoning step.
That's a perfect analogy. The notepad is the agent's scratchpad or memory store. This is a tangible piece of context that persists between LLM calls. The agent isn't just reacting to the immediate prompt, it's building a coherent mental model of the task over time. It can write down its intermediate conclusions, track what it has already tried, and refine its plan. This allows it to tackle complex, multi-step problems without getting lost or repeating itself, maintaining a consistent thread of logic.
And this is what allows for true coherence in long tasks. If you ask an AI to plan a complex marketing campaign, a simple prompt might give you a generic, high-level outline, but an agent with an adaptive loop can break it down. Step 1. Research target demographics using a search tool. It observes the results, then writes to its context. primary audience is 18 to 25-year-olds active on TikTok and Instagram. Step 2. Based on that context, it plans the next action. Generate 5 TikTok video concepts. It's a continuous cycle of think, act, learn, and record. The context is no longer just the input we provide, it's a dynamic workspace the agent itself manages.
That self-management is the key. It shifts the burden of maintaining state from the developer to the agent itself, powered by a well-designed context pipeline. But what happens when the problem is too big for one detective? What if you need a whole squad? This brings us to multi-agent collaboration.
This is where things get really interesting, and frankly, much more complex. When you have multiple agents, the core challenge is communication. How do they share information without creating complete chaos? If every agent broadcasts every thought to every other agent, you don't get collaboration, you get a cacophony. The context window would be instantly overwhelmed with redundant, conflicting, or irrelevant information.
So context engineering in a multi-agent system becomes about designing an effective communication protocol. It's not just about what information is shared, but who it's shared with, when, and in what format. This is where orchestrators become absolutely critical. You can't just let agents talk freely. You need a system to manage the flow of information.
Imagine a software development team with specialized roles: a front-end developer, a back-end engineer, and a database administrator. They don't all work in a single massive document simultaneously. That would be a disaster. Instead, they use a project management tool, a central hub. The back-end engineer completes an API endpoint, and instead of emailing the raw code to everyone, they update the status in the project tool and post the API specification. That's a structured, contextual update. The front-end developer can then pull exactly the information they need, the API spec, without having to wade through the back-end code.
Frameworks like LangGraph are essentially building this digital project management tool for AI agents. They act as a central blackboard or a state machine. One agent, let's call it the researcher, might be tasked with gathering data. It does its work and then posts a structured summary to the central graph. The orchestrator then routes this summary to the next agent, the analyst, whose turn it is to act. The analyst's context for its task is now perfectly curated. It contains the goal and the researcher's summary, not the raw search results or the entire history of the project. This prevents context overload and ensures each agent gets only the information relevant to its specific subgoal.
This allows for incredible specialization. You can have one agent that's an expert at database queries, another that excels at creative writing, and a third that's a ruthless code debugger. They pass structured artifacts, pieces of context, to one another, collaborating on a problem far more complex than any single agent could solve alone. The engineering challenge shifts from designing a single perfect prompt to designing the communication channels and the very structure of the information that flows between these specialized agents.
And until now, we've been implicitly discussing that information as text. But the world isn't just text. Our own human context is a rich tapestry of sights, sounds, and sensations. The next evolutionary step for AI agents is to integrate this multimodal context.
Absolutely. This is about expanding the agent's perception of the world. A text-only LLM is like a person trying to understand the world from behind a locked door, only able to read notes slipped underneath. Multimodality opens the door. Now the agent can see a picture, hear a command, or even process raw sensor data from a robot's camera. This fundamentally changes the kinds of problems an AI can solve.
The technical challenge here is significant. How do you translate a JPEG image or a WAV file into something an LLM, which fundamentally operates on text tokens, can understand? This is where techniques like joint embeddings or visual prompt generators come into play. Essentially, these are methods for converting non-text data into a tokenized representation that can be seamlessly inserted into the model's context window alongside the text instructions.
Think of a home assistant robot tasked with tidying up a room. A text-only instruction like "clean the living room" is deeply ambiguous. But with multimodality, the agent can access a live feed from its camera. Its context now includes both the text command and a visual representation of the room. It can see the clutter. It can identify a book on the floor. It can then reason, the instruction is to clean, I see a book on the floor, books belong on bookshelves. My next action is to pick up the book and place it on the shelf.
That's a powerful example of vision-guided reasoning. The image isn't just a piece of data, it's an integral part of the agent's reasoning context. This introduces new complexities, of course. There are challenges of alignment, ensuring the model correctly maps the visual tokens to the concepts in the text, and the sheer volume of data. A few seconds of video can generate a massive number of tokens, so techniques for summarizing or focusing on the most relevant parts of the visual feed become another layer of context engineering.
These concepts aren't just theoretical. They are being deployed in the real world right now. Let's talk about adaptive copilots and assistants, because they are prime examples of how these context pipelines create a persistent memory that makes interactions feel so much more natural and effective.
A great example is a modern coding copilot. When you first open a file and start typing, it has very little context. But as you continue, it's not just looking at the last line you wrote. Its context window is being dynamically populated with the entire file's content, symbols imported from other files, and perhaps even documentation for the libraries you're using.
And it gets smarter with each interaction. It's a form of memory. If you consistently use a certain coding pattern, the copilot starts to recognize it. It's not just completing your code, it's adapting to your style. Similarly, think of a smart scheduling assistant. The first time you ask it to book a meeting, it might ask for your preferences. Do you prefer morning or afternoon? You reply, mornings, and never on a Friday. A well-designed assistant will do more than just book the current meeting. It will perform a memory write. It will update its persistent context about you with the note, user prefers morning meetings, avoids Fridays.
The next time you ask it to book a meeting, its context pipeline will automatically retrieve that preference. The initial prompt it constructs for the LLM will look something like, user wants to book a meeting with Jane Doe. User preferences, morning meetings, no Fridays. Current calendar state, data from calendar API. The response you get feels magical. It's perfectly tailored, but it's the result of a robust context engineering pipeline that merges your request, your stored preferences, memory, and live data from tools, the calendar API.
This is the essence of building systems that learn and adapt to the user. The memory extends beyond a single conversation. It's a curated, persistent state that makes the AI a true assistant, not just a command line tool. It remembers, it anticipates, and it uses the full breadth of its context to serve you better.
Now let's take this one step further. So far, we've mostly imagined these agents running in a centralized cloud environment. But what happens when the agents and the sources of context are physically distributed? This brings us to the fascinating challenge of distributed context management.
This is the world of IoT, robotics, and edge computing. Imagine a smart factory floor. You have dozens of robotic arms, hundreds of sensors monitoring temperature and pressure, and a central logistics system. An agent running on one robotic arm doesn't have a complete godlike view of the entire factory. It has a partial, local view. Its primary context is its own sensor data. My current position is X, my gripper is holding part Y.
But for the factory to operate efficiently, that local context needs to be coordinated with a shared global context. For example, the agent on the robotic arm needs to know when the next autonomous guided vehicle will arrive to pick up the finished part. That information doesn't come from its own sensors. It comes from a shared back-end knowledge base that tracks all the vehicles.
This is where designing for partial views and synchronization becomes critical. The agent on the robot arm might periodically send a compressed summary of its state, its local context, up to the central system. Task A is 80% complete. The central orchestrator then updates the shared knowledge base. Another agent, controlling the logistics vehicles, can then query that shared context and plan its route accordingly. The context engineering here involves deciding what information is purely local, what needs to be synchronized, how often, and how to handle potential conflicts or delays in communication.
It's a constant balancing act between local reasoning and global awareness. You want the agent on the device to be as autonomous as possible to reduce latency, but you also need it to be integrated into the larger system. The design of the context, what data is stored on the edge, what is communicated, and how it's integrated into the shared state is the key to making such complex, distributed intelligent systems work.
So, as we've seen today, context engineering truly comes alive when we move from static information retrieval to dynamic, adaptive agents. Whether it's a single agent maintaining coherence through a memory loop, multiple agents collaborating via a central blackboard, or a distributed network of agents synchronizing their partial views of the world, context is the medium that enables intelligent behavior.
The key takeaway is that we're no longer just feeding information to a model. We are designing information ecosystems. We are building the note tags, the project management tools, and the communication protocols that allow AI agents to plan, act, and learn in complex environments, even integrating sight and sound to perceive the world more like we do.
The agent is no longer separate from its context. It actively shapes it. And as these agents become more autonomous and take on more critical tasks, a new set of questions emerge. How do we ensure they are reliable? How do we prevent them from making things up or drifting off course during a long interaction?
And that is precisely where we are headed next time. Having empowered these agents with rich, dynamic context, we must now turn our attention to the crucial issues of safety and stability. In our next episode, we will explore reliability and adaptation, preventing hallucinations and drift, where we'll discuss the difference between context failures and model failures, how to use context to ground our agents in reality, and how to build systems that are not just intelligent, but also trustworthy and auditable. You are listening to Context Engineering in LLMs, moving beyond prompt engineering. In our last discussion, we explored the incredible potential of AI agents and multi-agent systems, how they can plan, act, and even collaborate by manipulating their own context. We saw how they could integrate different modalities, from text to images, creating truly adaptive assistants. But this complexity introduces a critical, almost unsettling question. What happens when these sophisticated systems fail?
That's the crucial question. When an agent designed to manage your schedule suddenly books a meeting in the middle of your vacation, or a coding copilot confidently introduces a subtle but critical bug, where do we point the finger? For a long time, the default answer was, the model messed up. But we're beginning to understand that's often the wrong place to look.
Precisely. The focus is shifting. Today, we're dissecting the anatomy of AI failures in this new paradigm. We'll explore the distinction between a model failure and a context failure, which is where the vast majority of errors now originate. We'll delve into how poor context is the root cause of hallucinations and incoherence, and examine the strategies we can use to maintain an agent's focus over long, complex interactions to prevent what's known as contextual drift.
And once we understand the failure modes, we have to talk about how to prevent them. This means discussing the new frontier of robustness testing. How do you even benchmark a system whose performance depends on a constantly evolving information pipeline? From there, we'll get into the bedrock of building trustworthy AI, logging, auditability, and the emerging science of quality of context metrics. This isn't just about making systems work, it's about making them reliable and transparent enough to be trusted with mission-critical tasks.
It's a fundamental shift from treating the LLM as a magical black box to treating it as a powerful but predictable reasoning engine that is entirely dependent on the quality of its inputs. The failure is less often in the engine itself and more often in the fuel we provide it. This is the core of moving from prompt engineering to true context engineering.
Exactly. Let's start there, with this idea of context versus model failures. A true model failure is a flaw in its core reasoning or knowledge baked in during training. For example, if a model fundamentally misunderstands a basic concept of physics. But a context failure is different. The model might be perfectly capable, but it's been given incomplete, ambiguous, or incorrect information. It's executing flawlessly, but on a flawed premise.
This distinction is critical for engineers and developers. Blaming the model leads to a dead end. You can't easily fix the foundational model. But identifying a context failure is actionable. It means the retrieval system missed a key document, the prompt didn't specify a crucial constraint, or the agent's memory is out of date. The problem lies within the architecture you designed, not in the billions of parameters of the model.
Think of it like a brilliant surgeon. A model failure is like the surgeon not knowing how to perform a procedure. A context failure is like the surgeon being handed the wrong patient's chart. The surgeon's skill is irrelevant if the input data is wrong. They might perform a perfect operation on the wrong person because the context they were given was fundamentally broken. This is precisely what happens when an AI hallucinates.
Let's unpack that, because hallucination is a term that gets thrown around a lot. In this framework, a hallucination is often a direct symptom of impoverished context. The model is designed to fill in gaps and produce a coherent response. If its context window contains a question but no verifiable facts to answer it, it will bridge that gap with the most statistically probable information from its training data, which may or may not be true.
And that's where we, as context engineers, step in. We can prevent these fabrications by ensuring the context is never empty when facts are required. This is the essence of retrieval-augmented generation, or RAG, but taken a step further. It's not just about retrieving some data, it's about providing verified, up-to-date, and authoritative knowledge directly within the prompt. We can include guardrails like explicit instructions. Only answer based on the provided documents. If the answer is not in the documents, state that you do not know.
That instruction itself is a piece of context, a meta-instruction that governs the model's behavior. We can also embed sanity checks. For instance, if you're building a financial bot, the context could include a rule that any transaction over a certain amount must be flagged, or that a stock price can't be negative. The model doesn't need to have learned this. We enforce it at runtime by making it part of the immediate information environment.
This works well for self-contained tasks, but what about the challenge of maintaining coherence over a long interaction? This is the problem of drift. An AI assistant might start a conversation with a clear goal, but after 20 exchanges, it starts losing the thread, distracted by tangents or forgetting the original objective.
The technical reason for this is the finite size of the context window. As the conversation grows, older parts of the exchange are pushed out to make room for newer ones. The initial, goal-setting instructions can literally disappear from the model's view. It's like trying to navigate a maze but only being able to see 10 feet in front of you. You might forget the overall map you were shown at the beginning.
The solutions here are fascinating examples of dynamic context management. One powerful technique is summarization. You can have a separate process or even a call to the LLM itself with a specific prompt to periodically summarize the conversation so far. This compressed summary then becomes a permanent fixture at the top of the context window, a constant reminder of the overarching goal and key decisions made. You're effectively creating a condensed version of the map that always stays in view.
Another approach is to structure the agent's memory. Instead of a single long transcript, you might have separate slots for user goal, key constraints, and resolved subtasks. As the conversation progresses, these slots are updated. A subtask, once completed, can be moved to an archived log, removing it from the active context window to free up space while still being retrievable if needed later. This prevents the model from getting bogged down in details that are no longer relevant.
It's like cleaning your desk while you work. You put away the tools you're done with so you have space to focus on the task at hand. This kind of contextual hygiene is essential for building robust agents. But it also raises the next big question. How do we know if these strategies are working? How do we test the reliability of a system this dynamic?
Traditional software testing and even traditional model benchmarks fall short. An accuracy score on a static dataset doesn't tell you if your agent can maintain focus over a 30-minute troubleshooting session. We need new benchmarks designed specifically for context-driven systems. This means moving from single-turn question answering to multi-turn, stateful tasks.
We're seeing the emergence of exactly that. For example, there are memory retention tasks, where you give the agent a piece of information at the start of a long conversation and test if it can recall and use it much later. There are also multi-hop reasoning challenges, where the agent has to find one piece of information, use that to unlock a second tool or database, and then synthesize the findings. This tests the entire context pipeline: retrieval, tool use, and memory management, all working in concert.
And the evaluation needs to happen at two levels. There's component-level testing. Is our retrieval system pulling the right documents with high accuracy? Is our summarizer faithfully capturing the key points? But then there's the crucial end-to-end evaluation. Despite all the components working, is the final answer correct, consistent, and helpful? A user doesn't care if your retrieval accuracy is 99%, they care if the bot solved their problem.
This leads directly to the issue of trust. If a system fails, especially in a high-stakes environment like healthcare or finance, we absolutely must be able to understand why. This is impossible without meticulous logging and auditability of the context.
For every single decision an agent makes, we need a snapshot of the context window at that exact moment. What was the user's prompt? What documents were retrieved? What did the agent have in its short-term memory? What tool did it decide to call, and with what arguments? This creates an immutable audit trail. When something goes wrong, you can reconstruct the agent's thought process and pinpoint the exact piece of faulty context that led it astray.
This is non-negotiable for any mission-critical AI. It's about building in transparency from the ground up. Standardizing how this context is recorded is also vital. Every log entry should include not just the content, but also metadata, timestamps, version numbers of the data sources, which user was interacting with the system, and even a record of their consent for their data to be used in that context. Accountability requires traceability.
As we get better at logging and analyzing these contexts, we can start to move from reactive debugging to proactive quality control. This brings us to the really cutting-edge idea of establishing quality of context metrics. Instead of just hoping the context is good, we can start to measure it.
This is a game changer. Imagine being able to automatically score a context window before it's even sent to the model. We could develop heuristics for this. One metric could be context relevance, using something like an embedding model to measure how semantically related the retrieved information is to the user's immediate query. If relevance is low, the system could trigger a re-retrieval from a different source before proceeding.
Another obvious one is redundancy. LLMs are powerful, but they can get bogged down if you feed them the same piece of information 5 times in slightly different wording. A quality metric could identify and prune this duplicate information, making the context leaner and more potent, and also saving on token costs.
My favorite is the idea of context coverage. This metric asks, does the context contain all the necessary information to address the task? This is harder to measure, but you could train a small classifier model to predict whether a given context is sufficient. For an e-commerce bot, it might check if the context includes the user's shipping address, the item's stock status, and payment information before attempting to finalize an order. If coverage is low, the agent knows it needs to ask the user for more information.
These metrics, while still emerging, represent the maturation of context engineering from an art into a true engineering discipline. They pave the way for automated systems that can self-regulate the quality of their own information diet, pruning, refining, and enriching their context on the fly to maximize reliability.
So, it all comes back to a central theme. To build reliable and adaptable AI, we must shift our focus from just the model to the entire ecosystem of information that surrounds it. Preventing hallucinations and drift isn't about finding a better model. It's about designing a better context pipeline, one that is grounded, focused, and, crucially, transparent.
That transparency is the bridge to our next conversation. Once we've built systems that are reliable and auditable, we're faced with an even deeper set of questions. How do we embed our values, our ethics, and our safety rules into this context?
Exactly. Building a system you can trust is one thing. Building a system that is trustworthy in a broader societal sense is another. That means tackling bias, ensuring privacy, and designing explicit guardrails to prevent misuse.
And that is precisely where we will be heading in our next episode, as we explore the critical domain of governance, ethics, and safety in contextual AI. It's a journey from making systems that work to making systems that work for the good of everyone. Welcome. You are listening to Context Engineering in LLMs, moving beyond prompt engineering. In our last discussion, we navigated the complex challenges of ensuring AI systems are reliable and robust. We explored how to prevent hallucinations and model drift by focusing on the quality of context, essentially making sure our AI agents don't fail because of a poor information environment. But that raises a critical subsequent question. Once we've built a reliable system, how do we ensure it's a trustworthy one?
Exactly. It's one thing to build a powerful engine. It's another entirely to install the steering, the brakes, and the safety systems that ensure it can be operated responsibly in the real world. Reliability is the foundation, but trustworthiness is the structure we build upon it. Today, we're shifting our focus from preventing technical failures to embedding ethical and safety-conscious principles directly into the fabric of our AI systems. We'll be dissecting the governance of context, how we manage it, secure it, and hold it accountable.
We'll be covering some crucial ground. We'll start with how to embed safety guardrails directly within the context itself. Then we'll move into the persistent challenges of bias and fairness, looking at how the context we provide can either perpetuate or mitigate these issues. From there, we'll tackle the non-negotiable requirements of privacy and data compliance in a world where context can often contain sensitive information.
And we won't stop there. We'll also explore the mechanics of creating a transparent system through context auditing and provenance, which is like giving our AI a memory with footnotes. We'll then discuss the need for dynamic monitoring and fallback mechanisms, the emergency brakes for when things go wrong in real time. Finally, we'll look ahead to the importance of developing industry-wide context protocols and standards, the very frameworks that will allow us to build these complex systems safely and at scale. This isn't just about best practices. It's about laying the groundwork for AI we can fundamentally trust.
Let's begin with the most direct method of control, embedding safety and guardrails. The core idea here is that the context window isn't just a space for data, it's a control surface. We can use the system prompt or dynamically retrieved instructions to enforce operational policies at runtime. This is a fundamental shift from trying to train a model to behave in the abstract to giving it explicit, actionable rules in the moment of execution.
Think of it like a chef in a high-stakes kitchen. You don't just train the chef on general cooking principles and hope they remember every dietary restriction for every customer. Instead, for every dish, the ticket comes with explicit, unmissable instructions: allergy alert, no peanuts, low sodium, vegan. The context, the ticket, acts as a real-time policy enforcer. In AI, this means if you have a customer service bot, its context for a given interaction might include a dynamically inserted rule: do not offer discounts greater than 15% without manager approval, or under no circumstances should you ask for a user's full password. These aren't just suggestions, they are hard constraints that shape the model's response generation.
And this approach is incredibly powerful because it's both flexible and immediate. You don't need to retrain a multi-billion parameter model to update a policy. If a new compliance regulation comes into effect, you update the document or rule that gets retrieved and injected into the context. For instance, a financial advisory AI could have its context prepended with the latest regulatory disclosures required for a specific region, ensuring every piece of advice it generates is compliant without altering the core model. These safety filters become a dynamic layer of governance.
This also directly addresses the problem of fairness and bias, which is our next critical area. The old adage of garbage in, garbage out is exponentially more potent when it comes to context. An AI model can be perfectly unbiased in its architecture, but if its context window is filled with data from a skewed or narrow set of sources, its output will inevitably reflect that bias. The context is the lens through which the model views the world for a specific task. If the lens is warped, the picture will be too.
That's the crux of the issue. We're talking about curating the AI's informational diet. If a hiring assistant AI is given context from past job descriptions that are filled with gendered language, it will likely perpetuate that bias in the new descriptions it generates. Mitigating this requires a conscious and deliberate engineering effort. Strategies involve programmatically diversifying retrieval sources. When the AI needs information, the system should be designed to pull from a pre-vetted, balanced corpus of documents, ensuring it's not just drawing from a single, potentially biased perspective.
It also involves proactive sanitization of the context itself. For example, we can design systems that identify and anonymize sensitive attributes in the data before it even enters the context window. If the AI is evaluating resumes, a pre-processing step could strip out names, photos, and other demographic data that could trigger unconscious biases the model may have learned from its training data. We're essentially redacting the information that isn't relevant to the task and could lead to an unfair outcome. We can also implement monitoring systems that watch for correlations. If we notice that contexts containing certain demographic patterns consistently lead to negative outcomes, that's a red flag that our context sourcing strategy needs immediate reevaluation.
This leads us directly to the handling of sensitive data, specifically privacy and compliance. Context windows are ephemeral, but the systems that feed them, the memory stores, the databases, the user history logs, are not. Governance here is paramount. We are often dealing with personally identifiable information, proprietary business data, or protected health information.
The principles here are non-negotiable. First, data in long-term memory stores must be secured, meaning encryption at rest and in transit. Second is anonymization or pseudonymization wherever possible. A medical AI doesn't need to know the patient's name is John Doe. It just needs a unique identifier to track the case history. The context should only contain the minimum necessary information to perform the task. Third, and this is crucial, is consent. The system must be able to perform consent checks before pulling certain types of data into the context. For instance, before an AI assistant accesses a user's calendar or email to answer a query, the system should verify that explicit permission has been granted for that type of data access.
In heavily regulated industries like finance or healthcare, this extends to data residency and access policies. The context pipeline itself must be designed to respect these rules. A request from a European user should trigger the retrieval system to pull data only from EU-based servers. Access logs must be meticulously kept, detailing who or what accessed the data and for what purpose. The retention period for context is also a key policy decision. How long do you store a conversation history? The default should be no longer than necessary, in line with principles like GDPR.
This meticulous record-keeping is the perfect segue into our next topic, context, audit, and provenance. For any system that makes critical decisions, you need to be able to answer the question, why did it do that? With context-driven AI, the answer almost always lies in the information it was given. Traceability is everything.
Exactly. Context provenance means that every single piece of information in the context window is tagged with metadata about its origin. Where did this fact come from? Which database table? Which API call? What was the timestamp of the retrieval? Was it from the user's direct input or from a long-term memory store? This creates an audit trail, a breadcrumb trail that allows engineers, compliance officers, or auditors to perfectly reconstruct the agent's thought process for any given decision.
Imagine a medical diagnostic AI that suggests a particular treatment plan. If that decision is ever questioned, you need to be able to see the exact context it had. Was it working with the latest research paper retrieved from a trusted medical journal, or was it an outdated article from a less reputable source? Was a piece of patient data mistyped or misretrieved? Without provenance metadata, debugging becomes a black box nightmare. With it, you can pinpoint the source of a failure. It's like a citation system for the AI's brain. You can follow the footnote for every claim it makes back to the original source.
This audit trail is also indispensable for building trust with users. If an AI denies a loan application, the user has a right to an explanation. A well-architected system can use its context log to provide one. The decision was based on information retrieved from credit report X, which indicated Y, and market data from source Z. It demystifies the AI's decision-making process.
But what happens when the context becomes corrupted in real time? A data source could go down, an API could return a faulty response, or conflicting information could be pulled from two different documents. This is where dynamic monitoring and fallback strategies become the system's active defense mechanism. You can't just trust the context. You have to verify it continuously.
This is about building resilient systems. The agent should have a process for contextual self-awareness. It needs to monitor for anomalies. For example, if a financial trading bot suddenly receives stock price data that is orders of magnitude different from the last data point, it shouldn't just blindly execute a trade. The system should flag this as a potential context corruption. Other anomalies could be conflicting facts. One retrieved document says a project is approved, another says it's canceled.
And when an anomaly is detected, the fallback strategy kicks in. This is the system's emergency plan. The simplest fallback is to refetch the information from a primary, trusted source. If that fails, the system might discard the suspicious context and revert to a safe, default state. For a customer service bot, this could mean escalating the conversation to a human agent with a message like, "I'm having trouble accessing the right information to help you." For a medical AI, it could mean refusing to provide a diagnosis until the conflicting data is resolved by a clinician. It's the AI equivalent of a doctor saying, "I need to order another test before I can be sure." It's a mechanism to ensure that when in doubt, the system fails safely rather than proceeding with potentially dangerous actions based on corrupted context.
All of these mechanisms, guardrails, bias mitigation, privacy controls, auditing, and dynamic monitoring, are incredibly complex to implement on a one-off basis. As the field matures, the need for standardization becomes overwhelming. This brings us to context protocols and standards. We need a shared language and a common framework for how we structure, share, and govern context.
This is how any mature engineering discipline evolves. We don't have every architect inventing their own type of electrical wiring for every new building. We have standards, codes, and protocols that ensure safety, interoperability, and reliability. In AI, this could mean developing a standardized schema for context metadata. Every piece of context, regardless of the system, could carry a standard JSON header that specifies its source, timestamp, data sensitivity level, and user consent status.
A standardized format, like a Managed Context Protocol or MCP, would be transformative. It would allow for the development of plug-and-play governance tools. You could have a third-party auditing tool that can analyze the context logs of any MCP-compliant system to check for bias or compliance violations. It would enable interoperability between different AI agents, allowing them to share context in a way that is safe and understandable. It streamlines everything.
So, as we draw these threads together, a clear picture emerges. Trustworthy AI isn't an accidental property of a powerful model. It's a direct result of meticulous, principled engineering of the context that surrounds that model. It requires embedding our rules and values directly into the AI's information environment, rigorously curating the data we expose it to, and building transparent, auditable systems that can fail safely.
The ultimate takeaway is that context engineering provides the levers for control and governance. By managing the flow of information, we can guide the AI's behavior far more effectively than by simply hoping its initial training aligned with our goals. We are moving from being model trainers to being system architects, and the blueprints for these systems must have safety, fairness, and privacy at their very core.
And this is just the beginning of building truly advanced, responsible AI. Now that we've established the critical importance of a governed, trustworthy context, we can start to imagine what becomes possible when we scale these systems. What happens when an AI can hold not just a few documents, but an entire library in its context? Or when it can learn and update its own context over time?
That's precisely where we're headed in our next episode. We will be venturing into the future of context-aware AI, exploring the push towards ultra-long context windows, the concept of dynamic, self-organizing memory, and the new cognitive architectures that could lead to truly intelligent, collaborative AI systems. We'll be moving from governance to cognition. Join us next time. Welcome, and thank you for joining us on Context Engineering in LLMs, moving beyond prompt engineering. In our last discussion, we navigated the critical landscapes of governance, ethics, and safety, the guardrails that ensure our AI systems are trustworthy. We established that context isn't just about performance, it's a mechanism for control, fairness, and compliance.
Exactly. We built the foundation for responsible AI, but with that foundation secure, a compelling question arises. What do we build on top of it? If we have the tools to make AI safe, how do we then make it truly intelligent, truly cognitive? Where does this road lead?
That is precisely the question we're exploring today as we look to the horizon. We're moving from the necessary constraints of today to the boundless possibilities of tomorrow. We'll be peering into the future of context-aware AI, a future that hints at something much closer to cognitive machine intelligence.
It's a journey from building well-behaved systems to architecting genuinely aware ones. We'll be covering some fascinating territory: the push toward ultra-long context windows, what it means for an AI to have a dynamic, self-organizing memory, and how new cognitive architectures are drawing inspiration directly from neuroscience.
We will also explore the emergence of collective multi-agent intelligence, where AI systems collaborate by sharing context. Then we'll circle back to our previous conversation by examining how context itself can become the primary mechanism for value alignment. And finally, we will look at the evolution of our role in this process through human-AI co-creation.
These aren't just incremental improvements. Each of these threads represents a potential paradigm shift in artificial intelligence. They build on everything we've discussed about retrieval, memory, and tools, but they project those concepts onto a much grander scale. It's the difference between building a better engine and envisioning a whole new form of transport.
Let's begin with the most immediate frontier: scale. For years, the context window, the amount of information a model can consider at once, has been a fundamental bottleneck, but that is changing rapidly. We're seeing research pushing context windows to hundreds of thousands, even millions of tokens.
It's hard to overstate what a monumental shift this is. Imagine trying to understand a complex novel by only being able to read one page at a time. You'd constantly lose the plot, forget characters, and miss the overarching themes. That's been the state of LLMs. They have a form of short-term memory loss.
And the technical solutions are quite elegant. We're moving past the quadratic scaling limitations of traditional attention mechanisms. Techniques like linearized attention, which approximates the full attention matrix, and advanced compression algorithms allow models to handle vastly larger inputs without a corresponding explosion in computational cost.
The analogy I keep coming back to is the difference between a personal library and having the entire Library of Alexandria instantly accessible and fully indexed in your mind. With an ultra-long context, an AI could be fed a company's entire internal knowledge base, every document, every chat log, every line of code, and operate with a complete, holistic understanding of the organization.
Or consider a personal assistant AI. It wouldn't just know your schedule for today. It could, with permission, process your entire digital life, every email, every note, every conversation, to build a truly deep longitudinal understanding of your goals, preferences, and relationships. The context becomes a lifetime.
This capability transforms the very nature of the tasks we can assign to AI. Instead of asking it to summarize a single document, you could ask it to identify emergent, cross-departmental risks over the past 5 years. The AI is no longer just processing information, it's synthesizing wisdom from a vast sea of data, all held within its active attention.
But simply having a bigger container for information isn't the endgame. The information within that container needs to be alive, to be current. This leads us to the next evolution: dynamic, self-organizing memory.
This is where we blur the line between inference and learning. Traditionally, a model is trained and then it's deployed. Its knowledge is frozen in time. Retrieval-augmented generation, or RAG, was a huge step forward, allowing us to fetch fresh information at runtime. But the model's internal memory, its parametric knowledge, remained static. Dynamic memory proposes a new model. What if the AI could update its own knowledge base and memory structures based on new information it encounters during deployment? It's a form of continual learning, but happening on the fly, within the context engineering framework.
Think of it like a human learning a new skill. The first time you try to bake bread, you follow a recipe, a retrieved document, very closely. But as you bake more, you start to internalize the process. You learn how the dough should feel, how the crust should sound. You're not just retrieving the recipe anymore. You're updating your own internal model of how to bake. You are adapting your own memory with experience. A future AI agent could do something similar. It might retrieve a document stating a fact. But if it later encounters contradictory information from a more reliable source, it wouldn't just use the new information for one answer. It could be architected to revise its own memory store, flagging the old information as outdated and promoting the new fact. The context system becomes a living, evolving knowledge graph.
This creates a powerful feedback loop. The AI's actions generate new information, which in turn refines its memory, which then informs its future actions. The context is no longer just something that is fed to the model, it's something the model actively curates and refines for itself. It begins to look a lot less like a database and a lot more like a genuine learning process.
And that learning process could become even more sophisticated. This brings us to ideas inspired by cognitive science and neuroscience, the concept of cognitive architectures and internal workspaces. We're not just thinking about how to get information into the context, but how the AI internally manages and reasons with that information.
This is one of the most exciting areas of research. Current models process their entire context in a somewhat uniform way. A critical instruction might be treated with the same initial weight as a trivial piece of data. Human cognition doesn't work like that. We have mechanisms for attention. We can focus on a specific task, pull relevant memories into a mental workspace, and ignore distractions.
Future context systems might mimic this. Imagine an AI with different cognitive modules. One module could be a scratch pad for short-term reasoning. Another could be a long-term memory store. A director module could then learn what information to pull from these various sources into an active workspace based on the task at hand. This is a form of directed information selection.
It's the difference between having a messy desk with every document you've ever owned piled on top versus having a clean workspace where you've deliberately placed only the 3 or 4 items you need for your current project. It's about focus. This would allow an AI to tackle much more complex, multi-step problems. It could decide to focus on retrieving historical data first, then formulate a hypothesis in its workspace, then seek out new information to validate it, all without explicit step-by-step programming from a human.
This internal management of context could lead to emergent reasoning capabilities. Instead of just following a chain of thought prompt, the model could develop its own internal monologue, its own strategies for solving problems, by learning how to best manage its own cognitive resources. We are now talking about architecting the very thought process of the machine.
And what happens when these machines, with their own internal thought processes, start to interact? This leads to the next logical step, collective multi-agent intelligence.
Precisely. So far, we've mostly discussed a single agent or system, but the real world is a multi-agent environment. The next frontier is creating webs of interconnected agents that don't just communicate, but share and build upon each other's contexts.
This is where context engineering becomes the literal language of collaboration between AIs. Imagine a team of specialized agents working on a complex scientific discovery. One agent is an expert in genomics, its context filled with protein folding data. Another is an expert in clinical trial data. A third understands pharmaceutical supply chains.
In today's world, a human would have to query each one and synthesize the results. In a future system, these agents could share context directly. The genomics agent could pass a potential protein target into the shared context. The clinical trial agent could then access that context, cross-reference it with its own knowledge, and append data on patient populations. The supply chain agent sees this and begins modeling manufacturing feasibility.
It's like a silent, high-bandwidth conversation between expert minds. The shared context becomes a collective consciousness for the group. This could lead to emergent problem-solving capabilities far beyond what any single agent could achieve. The group becomes a single, cohesive intelligence, anchored by a shared, dynamic understanding of the problem space. We would be engineering the environment for a collective AI mind to form.
But as we build these increasingly powerful and autonomous systems, whether individual or collective, the question of alignment becomes more critical than ever. This brings us full circle, back to the themes of safety and ethics from our last conversation. How do we ensure these cognitive systems act in accordance with human values?
This has traditionally been seen as a problem of model training. We try to bake values into the model's parameters through techniques like RLHF. But that's a static approach. Human values and societal norms evolve. A model trained on today's values might be misaligned tomorrow.
Context offers a much more dynamic solution. Instead of trying to permanently embed values in the model, we can make those values a persistent, updatable part of the agent's context. The agent's core instructions, its constitution, can be a living document that is retrieved and included in every decision-making process.
This is incredibly powerful. Think of it as a living contract between the user and the AI. My preferences, my ethical boundaries, my personal goals, these are not just things I stated once during setup. They are part of the context, and I can update them. If my financial goals change from aggressive growth to capital preservation, I can update that preference in my context, and the AI financial advisor will naturally adjust its recommendations without needing to be retrained.
The alignment isn't a one-time event during training, it's a continuous process at runtime. The context window becomes the channel through which we steer the AI, ensuring its decisions remain congruent with our evolving intent. It shifts the burden of alignment from the model's creators to the system's users and operators, where it arguably belongs.
And this brings us to the final piece of the puzzle, our own role in this future. If we are to become the curators of these complex information environments, we will need better tools. That is the future of human-AI co-creation.
Absolutely. Writing complex system prompts and designing intricate RAG pipelines in code is the current state of the art, but it won't be the future. We are already seeing the beginnings of tools that allow for more intuitive context design.
I envision visual context design interfaces, almost like a digital canvas or a flowchart. A developer or even a subject matter expert with no coding skills could literally draw the flow of information. They could drag and drop knowledge sources, create rules for when certain memories should be prioritized, and visualize how the context changes in response to different user queries.
We could even have AI-assisted context visualization. The AI could help us see the agent's thought process, highlighting which pieces of context were most influential in a given decision. This would be invaluable for debugging, auditing, and refining the system's behavior. It turns the black box of the model's reasoning into a transparent, interpretable flow of information.
This co-evolution of methodology and tooling is how context engineering will mature from a specialized discipline into a fundamental pillar of how we interact with and build alongside AI. It's not just about us telling the AI what to do anymore. It's about us collaborating with the AI to build its understanding of the world.
It truly is a profound shift. We've journeyed in this podcast from the simple act of writing a better prompt to architecting a machine's entire information reality. We've seen that context is memory, it is tools, it is the foundation of safety, and, as we've discussed today, it is the pathway to more cognitive and aligned artificial intelligence.
The key takeaway is that the future of AI development is less about being a programmer and more about being an architect, a curator, or even a teacher. We are designing the environment in which intelligence can emerge and flourish. The focus moves from the model itself to the rich, dynamic world of context we build around it.
The journey of context engineering is really just beginning, but it's clear that it represents a move towards a more mature, robust, and ultimately more collaborative relationship with artificial intelligence. Thank you for joining us on this exploration.